Okay, we are gonna start with DC machines. And for DC machines, we are gonna see the Lorentz law. This says that a force is applied is applied when we have a conductor of length L in a field. So whenever we have a current in a conductor that is in a field, we are gonna have a force. So we are gonna have, for example, here an electric current going this way. This is the current. We are gonna have a field going this way. So by the right hand rule, when we have two vectors that are perpendicular, perpendicular to each other, the result is gonna be perpendicular. Now we always try to go uh, from the shortest route. So if we go from I to B, because that's how we are doing the cross A B. So when we go out I to B and we are going anti-clockwise, the result is gonna be positive. And the other way around, if this I were going like this, the result will be negative. Okay, now parting from this, uh, you probably have seen before the model of a DC motor that we are gonna have here one of the magnets with the north pole. Here we are gonna have the other magnet with the south pole, and here we have the conductor. So not gonna spend a lot of time with this. Uh, just as a reminder, well, if we follow this, even we have a current going this way, this is gonna experience a force going upwards, and here is gonna force going downwards. This is gonna be the force. But this is only true if these terminals stay the same. That's why we have a commutator here that allows to change, because you can do the tough experiment figuring out what will happen with the motor when it goes if we don't change the the currents here. But basically it's just gonna go like a pendulum. It will try to go from one to another and go reverse, so it will not rotate. So from this, what I want you to get is like the rotor experience an AC current. Even though we have a DC source, the coil in the rotor always experience an AC current. And that's why and this is important to keep in mind, because when we do the control and everything, this is gonna play a part of why the formulas look of how they look. Now, what about we don't have a current in the conductor, but we have a field. We just have the field, and then we, instead of having a force, we have a velocity in the conductor in a field. Well, that is Faraday's law, and we have here we will have an EMF produced. That is the cross between the velocity and the field times the length of the conductor. Now if we translate this into rotational motion, we are going to have that our EMF is going to be, our velocity is going to be an angular velocity. We are going to have the beta. We know that beta, the fuel intensity, is expressed in flux times area, and we are going to have the length of the conductor. So let's think about the things that we got here. We have the area and the length, and these are parameters that will depend on how many poles we got, how many coils, but all of the stuff is made into the motor and cannot be changed. When it's set, is set. So all of them are usually placed into a constant. Okay. And then the things that change is gonna be the flux and the angular velocity, angular speed. Okay, so this will be the formula for EMF for this for a DC motor. Now, what would be the torque? Well, we know that torque is equals to the force times the radius. And we know that what we saw here is that our force is this. Our force is gonna be equals to our BL times our current in our armature times the radius. And again, we know that flux B is equals to the flux tangent area. We are gonna have L, we're gonna have the current, and we're gonna have the radius. And again, the area, the length, and the radio, they are all parameters that are built into the motor, so we're just gonna call them KT. And we're gonna have the torque is equals to KT times the the torque constant, or the motor constant, times 5 IA. Okay. Now, in many books or in exercises that we're gonna do, we're gonna have Ka, that is the constant when we did the EMF, times 5. They are gonna put it in a single value, Ka. And the same for the torque. They are gonna put it K5 into a single value of Kt, capital T, or Kb. And these two are typical equal, the same, yeah. So when you see K, we are typically talking about both of them. Okay, so now that we got the voltage formulas and the torque formulas, we can see here the voltage. Okay, the voltage, the equivalent circuit. Okay, so this is the EMF produced for the rotation of the rotor. So what we do here, when we rotate this, we produce an EMF, and it always will be opposite to the voltage that we apply. So that's what we got here. Okay, so if we do what we have always done about the loop in the voltage loop, we're gonna have that the terminal voltage is IA. IA is the current going here, the current in the armature, times our resistance in the armature, plus our inductance, so our voltage in the inductor, plus EA. Okay, we seen before, EA is equals to a constant that we're gonna call Ka, phi omega. And the developed torque. Now, torque is a tricky concept. It could mean many things depending of what. I mean, torque is the force times the radius. But the developed torque or the low torque, and there are different kind of torques that we have talked. So the developed torque is the sum of all the different torques. The torque produced by the motor, the torque lost by the load, and the torque lost by the windage or friction. All those uh, are different kind of torques. So for now, I'm just gonna write here TD for developed torque, assuming that there are no other torques. So this is like a general equation for the torque. Now, if we think about the steady state, model, well, then we just need to write the values in capital. So this is now capital AA, meaning that it is not changing, plus in a steady state, well, this will go to 0 because the derivative will go to 0, and we're gonna have our capital EA. And we know that EA is just our constant value, K Ka times phi omega, our speed. So now that we have our torque and our voltage equations, well, for torque it's going to be the same. We're going to have K phi times Ia. Now that we have our torque and our voltage equation, our developed torque, the torque that is show the sum of all the torques. Uh, so let's try to find this. What would be the speed? What would be the formula for the speed? Okay, so we see that here in these two formulas we have Ia. So we can, for this one, just solve for Ia. So we're gonna have our low torque over our chi phi. Okay, so let's figure out the speed for our low torque. That's why I mean that this is like a general formula. Okay, so we are gonna have here the Bt is gonna be equals to TL over K phi over times Ra plus K times 5 omega. Okay, now we can solve for speed, and we are going to have Pt minus TL Ra over chi phi over chi phi, and this is equals to chi phi Bt minus TL Ra over chi phi over chi phi. And finally, we can say that we have an omega of, well, this is like 1 here, so this is 2 squared. We're gonna have chi phi. So we know that we're gonna have chi phi squared here when we do this, and we have a chi phi here, so we are gonna just cancel those two. We're gonna say Pt over chi phi minus TL over, well, for this one it does not cancel, times Rr over chi phi squared. So now we have figured out our voltage, torque, and speed formulas for our DC motor. And this is a separately excited DC motor. Okay, so this is saying that the low torque is equals to chi phi Ia. I talked before about the different types of torques. So just a reminder that force is equals to mass times acceleration, and acceleration is the derivative of velocity. So if we change this into torque, that is a rotational, in a rotational, yes, we are gonna have that instead of mass, we are gonna have moment of inertia, and instead of the derivative of voltage, we're going to have velocity, speed, we're going to have the derivative of angular speed. And we know that if we want friction, the torque due to friction, then we have our friction coefficient B, and J again is our moment of inertia, and we have that the developed torque is all our torques added. Okay, and here we say that the power is equals to our torque times our speed. So our low torque times our speed will give us our mechanical power. That's what we had said before with our induction machines. So that was just a reminder. So clarify Ia equals to our friction coefficient times our angular speed. Okay. So now that we have reviewed all of about the DC motor, we can start doing some exercises. First, we have here Here they are asking us for the PM, our friction coefficient. Okay, so we know our formula for our speed is terminal voltage K5 minus RA K5 square times our load torque. Okay, so let's figure out what will be our speed. We need our speed because our formula uh, to find our friction coefficient, we are gonna need the speed. Okay, so we know that this will be a conversion load torque is approximately okay. So let's find our equation here. Okay, so they're not giving us the value of load torque, but they are giving us the constant value and the speed for this. Oh no, they are just saying that speed is omega r. So let's write whatever we have right now. We know that omega is our terminal voltage that they are giving us, yes, 6 volts. K5, they're not giving us the flux, they're just giving us the whole value of K times 5, so 0.01 volts is radians. No, I'm just not gonna write the whole unit for space. Minus RA, they're saying that is 8 ohms, and here is the same, 0.01 square. And now we need to find our TL, but they're saying that our constant is 5 times 10 to the minus 6 times omega r. Okay, so from this we can calculate our omega. So from this part, for the first part we're gonna get 600. For this one, all of this multiply and the division is 0.4, and we're gonna get omega r here. Well, this is also omega r. Now we are gonna have that omega r plus 0.4 omega r equals to 600, and we can say finally that our omega r is 600 or 1.4 equals to 420.6 radians per second. So remember, omega is always in radians per second. If they give you any other units, you need to change it first to radians per second. Okay, let's do the next exercise. Here we need to find the KB, the BM, and the RI. Okay. But what are they giving us? They are giving us EA, 7 volts. They are giving us omega, but they are saying R over mean, and we need to change this to radians per second. So I guess this is radians. Anyways, we multiply by 2 pi over 60 equals to 400 radians per second. And that's it. That's what they're giving us. Okay. So KB, if you remember, KB is how we write our flux times our constant, and that's what they want us to find. So one of the formulas that has this. So because we have here the terminal voltage, we can use the formula of EA equals to chi5 omega to find our chi5, because now we have our omega 2. So we can say that our QV, KV is equals to EA over omega equals to 7 volts over 400 equals to 0.175 volts over radians, or the unit that we saw before. Okay, so this is our kV. Now to find our, let's find AR first. That is a little bit easier. So we have our initial formula for speed, and here we can see AR. Now let's try to simplify this a little bit to get AR. So we can say that omega is equals to Vt kt5 minus IR over k5 squared, and let's say the low torque is ki phi ia. So from this we can cancel just one of this and this, and we can get omega equals to Vt minus AR ia over k5. So we can say that omega k5 equals to Pt minus RIA. So we can say that our RIA is equals to Pt minus omega k5 over IA. Another way of writing this is omega Bt minus EA, because this is EA, over EI. So kind of makes sense that the difference in the voltage over the current is our resistance. So we can plug the values that we have. So we have here for our terminal voltage, now that we change our speed to 650, is going to be 12 volts minus our speed, no, minus our speed that we calculated here. No, this is our kV. Oh yeah, this part over here times our speed, that is now 650. So this is if omega is 650. So we divide by IA, that is they gave us 0.1 amps. So we get a resistance of 6.3 ohms. Okay. Now we need to find the torque due to the friction. So if we have no load, all of the torque generator is the torque. The torque that we are generating is the friction. So we have the RB, our friction coefficient, and our omega is equals to chi phi Ia. So we have our friction coefficient times our omega, that is 650, is equals to our k phi that we figured out before, times our current that is given. And from here we can say that our friction coefficient is just 2.7 times 10 to the minus 6 Newton meters over radians per seconds. Okay. Okay. Now for this exercise, they are asking us for the friction coefficient again. Well, let's see what they're giving us now. They're giving us the moment of inertia, okay. They're giving us our KT. So KT is, we know that is our torque constant and array. Okay, so first they're saying that this is the speed with no load. So we know that this is the speed with our friction coefficient. So we have 350, we multiply by 2 pi over 6 to get radians per second, and we have here 351 radians per second. So we know this is the speed at which there is no load, so we know that whatever we are generating in torque, it might be for the friction. So we know that our friction coefficient at our speed is equals to K5 IA, formula that is always there. So just like the last example, 351 equals to our K5. They're giving it here as KT 1.1, and that's 10 to the minus 2. So if they're giving you volts over radians per second, they are giving you the whole K time the flux. And then we multiply by our current that is also given 1.5 here. And so we can calculate our P to be 6.03 times to the minus 6. Okay. This is newtons per meters over radians over seconds. Okay. Let's keep going with the next one. For this same machine, if the permanent magnet is if the same machine is operating with a rated applied armature voltage and a low torque, okay, now they're giving us the low torque. So first, we know that our efficiency is equals to the power in and the power out, or the power out. And we're gonna need the power in. So what is the power in? The power in is this, we can get, we have the speed with the developed torque. Okay, that's when we have a speed with our developed torque, we're gonna have a current, and the current we can use to find the power. So we know that the developed torque is the sum of the low torque plus our friction torque. So we're gonna have here a TD of, they are just giving us the low torque, and this is plus what we just find out for our friction coefficient, that is this multiplied by the speed. So we need to find this speed because this will be the speed for our developed torque. So we can say that omega is equals to Vt over K5 minus Ra over K5 squared times our developed torque. Okay, so let's start plugging everything that we got. We have omega equals to our voltage that is given, 6 over K5, 4.1 instead to the minus 2 minus our A is given to 7 over the same thing square, and all of this multiplying what we just found here for our developed torque. Okay, so let's simplify each part. We're gonna have here 425.53 minus 124 minus, this is 124 minus 0.2113 omega. So if we just simplify everything and solve for omega, we are gonna get 248.7 radians per second. So now that we have the speed, we can calculate the current. We figured out before that our resistance was our terminal voltage minus our K5 over IA. That's what we just figured out over here. Just let me check that this, yes, this is what we found here. So when we plug the values, it's going to be 6 minus 1.41 times 10 to the minus 2 times 243.7 over 7. Oh, wait. Okay, now I see why this look weird. We don't want AR, we want IA. So this is gonna be VT minus K5 over RA. Okay, now it makes more sense. And of course, now that I look at the formula, I know that we're missing our omega. Okay, now we can say that this is equals to our VT that is given 6 minus 1.41 times 10 to the minus 2 times 243 times 7 over 7, and we get our IA of 0.3557. Okay, so our power in is gonna be equals to our voltage and our current, and we have our voltage of 6, we have our current of this, so our power is 2.13 watts. And now our power in mechanical, we seen before, that is just our torque times omega, and this is with the speed at with the low torque. So we have a P out of 353 times 10 to the minus 3 times 248.7, and we just do the calculation and we know that our power out is just gonna our efficiency is gonna be our power out over our power in times 100%, and this is just gonna be 41.3%. Okay. I hope this helps. That's it. Oh, I just noticed that here I had made one mistake before in this formula. It is power out over power in. So before I had written it the other way around. So I'm sorry about that.